Hey, all you cool cats and kittens. This is Mr. Nicholson, and I am going to be talking to you about geometric sequences today. This is part of the reading notes that you could just read on your own, but if you needed kind of a video explanation, here it is. I believe Mrs. Gerber did the arithmetic sequence video, but I thought I'd do the geometric sequence one. So let's get started on this. Pretty basic. What we're talking about is a list of numbers. But in this case, the pattern of these numbers is that something is being multiplied every time. So it's similar to exponential equations because exponential growth and decay uses that type of formula. So we're not adding every time. That's an arithmetic sequence. Instead, we are multiplying. So look at example 1. We have 3, 6, 12, 24. If you look at the pattern is that we are doubling every time. We are multiplying by 2. So we need to look at how does that look as an equation, all right? Because we're not in elementary school. We're not even in junior high where we just look at patterns by number. We want to know a formula, an equation that can get us any term in the sequence. So we first look at example 1, and they're just going to give you the equation for that. It's 3 times 2 to the n minus 1. But if we break it down, what we see is the 3 is very specific. It's actually the first term. So that number every time when you have a sequence, that term, in this case 3, that's going to be your first term in the sequence. The 2 is going to be the number you're multiplying by. So in this case, we're doubling every time. We're taking each number in the sequence times 2 to get the next term. And then in this case too, the n minus 1, that pretty much always stays, right? So like if we wanted to know the very first term in the sequence, if we did term 1, we would do n minus 1. So 1 minus 1 is 0, and therefore 2 to the 0 is 1. We can get that first term. So that's why we have n minus 1. We don't want term 1 being 3 times 2. We want it 3 times 1. Okay, so that's how we would get that. Let's do this. Let's try and figure out if we can get an equation for number 2. So if we look at that pattern of this equation, what we want is, well, we'll call this one z, because z is a really cool letter. Z sub n, or z of n. Okay. So in that case, the equation z of n, we want to start with our first term, so 99, times our multiplier, but that's not 2, obviously, here. We're not taking 99 times 2 to get 33. We're actually dividing by 3 to get 33. And that's a little tricky because we cannot use division in our equation. We have to multiply. But hopefully you remember that instead of dividing by 3, it's really the same as multiplying by a third. Right? We can do that. We can substitute that. So that factor that we're multiplying by is 1/3. So now we have our first term and our multiplier, and our exponent is going to stay n minus 1. So there you have it. We have our first term, what it's being multiplied by. In this case, so again, if you're dividing, if it looks like our numbers are getting smaller and smaller, like in 2, we still have to say we multiply, but we're going to multiply by a fraction. In fact, if you go down further into these notes, it's just showing the breakdown of n is 0. Well, the exponent is 0, so n, first term, n minus 1 is 1 minus 1, and then 2 minus 1, 3 minus 1. So this is just giving you a breakdown of how that would come to be. At the very bottom, though, this is a really nice spot to go to if you're just trying to bounce back and forth. This is the general formula. Now, arithmetic, I'll leave that to Mrs. Gerber. Geometric, though, here's where, remember I said we have the equation is equal to our first term in the sequence, in this case, g sub 1, times our common ratio. That was the term I couldn't think of. I just thought I would keep calling it the multiplier. The official term for that number that we're multiplying by every time is the common ratio. So let's pretend like we go back in this video, and every time I said the multiplier, you put in the words common ratio, but that is the number that is being multiplied every time. It is multiplied every time. It doesn't say divided or multiplied. And that's why we had to have fractions, because we have to multiply. And then here, this n minus 1, the n is going to be what term number? So if I wanted to find the 6th term in this equation, I would take 6 minus 1, and then I would raise 1/3 to the 5th power. So 3 to the 5th, 1 over 3 to the 5th times 99. You can see that that's getting smaller and smaller. As 3 gets bigger and bigger, the whole thing is getting smaller and smaller. So this in fact would converge. We would say this converges to 0. Question 1, though, this number is getting bigger and bigger and bigger. We have no end in sight. This number is just going to keep getting bigger and bigger. So we would say that this one diverges. Okay, so if the terms get smaller and smaller, I'll give you an example. So here's example 1, where 3 and then 6 and 12, 24, those numbers get bigger, bigger, bigger. They're not heading anywhere particular. They are just going to infinity. So that is why that one diverges. If we go back and look, well, we'll turn this one off, turn this one on. Oh, why did that not work? Really doesn't like that, does it? Okay, well, we're just going to do this. There, it turned it on. Okay, so now we're going to graph, and red is example 2. Example 2, though, as you see, it is getting closer and closer to a particular number in the y value as it goes larger in the x. So this one converges. And that's why we can say it converges to 0. So that's it. Sorry it took so long, but hopefully that helped, and we know how to identify it, how to put it into an explicit formula, as well as whether it diverges or converges. So good luck out there.